Hi everybody, and welcome to Thursday's class. First thing we're going to do is go over the quiz. Problem number 1 was worth 5 points. Total quiz was worth 15 points. Problem number 1, you have this quadratic function y equals 3x squared minus 6x plus 2. You're asked to find the vertex, the y-intercept, and graph the parabola. Okay, I can look right there and see that my y-intercept is 2, so we can fill in that blank. Then to find the vertex, we use the formula x equals minus b over 2a, which was provided to you on the quiz. I plug in, b is negative 6, a is positive 3, simplify and I get 1. So we know that the vertex occurs where x is 1. So I take the equation and plug in x equals 1, and I calculate the corresponding y value, which turns out to be negative 1. So I can fill in this blank here. The vertex occurs at 1, negative 1. I plot the y-intercept, I plot the vertex. It's clear that the parabola fits in like this. Of course, it opens upwards because a is a positive number, and I get that parabola right there. For number 2, we're asked to solve a quadratic equation. So I try factoring. You can use any method, but I tried factoring, otherwise I would have gone to the quadratic formula. So I use our method here. I drew an arrow to go over here to my side work. 3x squared times minus 4 gives me negative 12x squared. Is there a way I can break up minus 4x squared so that it multiplies out to be negative 12x squared? Yeah, after some trial and error, I arrive at negative 6x times 2x. That gives me my minus 12x squared, and it adds up to minus 4x. So I now know how to break up that middle term. The minus 4x, I'll write it as minus 6x plus 2x. Then I group like this. Looking at the first group, I see that I can factor out a 3x. Looking at the second group, I can factor out 2, leaving x minus 2 in each case, underlined in the green there. So I can factor out that x minus 2, and I arrive here. I set each factor equal to 0 in order to solve the equation. X minus 2 equals 0 gives me x equals 2 as one of my roots. 3x plus 2 equals 0. That gives me x equals minus 2/3. I do a quick check over here. I'll try x equals 2, since that's easier to work with than using a fraction. I plug it in. Will I get 0? Yes. So that one checks, so I'm pretty confident the other one's correct too. And that's how we do number 2, also worth 5 points. And finally, problem number 3 is a piecewise defined function. F of x equals x squared when x is between 0 and 2, including the endpoints. Else, it equals minus 3x plus 1, where x is between 2 and 5, excluding both endpoints. And we're also asked to find the domain. Well, if I look at this, I say, okay, f of x equals x squared, that's my familiar parabola that opens upwards and its vertex is at the origin. It's the simplest parabola of all. So if I plot the endpoint where x is 2, I get 2 comma 4. And of course, starting at 0 starts me off at the origin. So I have this piece of my parabola. That's ranging from 0 to 2 on the x-axis. Then, starting just past 2, I'm going to use this formula. Now you might realize, oh, this is a linear equation. The slope is -3. The y-intercept is +1. So it has to be a steep line going downwards as we go from left to right, going through y equals 1. But of course, our domain for this portion of the function is restricted between 2 and 5, excluding the endpoints. Well, you could draw your graph like that, with that piece of reasoning that I just showed you, being careful to put a hollow dot at the beginning and at the end. Or, if you didn't want to do that, you could plug in two numbers that are in the domain here. So 3 and 4 are both between 2 and 5. If I plug them in, I get these y values, and I'm able to plot these 2 points on my graph. And then that determines the straight line, which can then be completed. You could even plug in x equals 2 and x equals 5, although strictly speaking, they're not in the domain for this part of the function. But, you know, it'll show you the 2 endpoints, but we have to leave them as hollow dots. So finally, we're asked to fill in the domain. Excuse me. I see x starts at 0, including 0, goes up to 2, and then from 2 it goes up to 5, but it excludes 5. So the domain is the half-open interval from, or half-closed interval, I guess you could say, from 0 to 5, including 0, excluding 5. Okay, so that was your remaining 5 points. Let's get on to today's lesson. Today's lesson is section 4.2, combining functions. It's kind of a short lesson, but difficult. It involves a real abstract concept and a very important concept. First, we're going to see how to combine functions using operations. Look at page 263 in your textbook. What could it possibly mean to add two functions? We add numbers. Functions are correspondences, they're not numbers. They're ordered pairs. Okay, well, it can mean whatever we define it to mean, but we want to come up with a definition that makes good sense and is consistent with the rest of our system. The definition that mathematicians came up with is this. If you have two functions, f of x and g of x, if you want to talk about the new function, f plus g, it's defined to be f of x plus g of x. F plus g of x equals f of x plus g of x. Let's see what that means. In example 1, we're given these two functions. In part A, we're asked to add the two functions and come up with f plus g of x. Our definition tells us that it equals f of x plus g of x. Substituting, I know that f of x is the same as x cubed, g of x is the same as x minus 1. That's given up here. So, I throw the parentheses away and simplify, and this is where I arrive in simplified form. Now let's look at part B. In part B, you're asked to find f minus g of x. Well, still on the same page there, 263 I believe it is. You see the definition for combining two functions via subtraction. And it's just what you would expect, I think. Just replace the plus signs with the minus signs and there you have it. F minus g of x is equal to f of x minus g of x. Okay, we're going to use the same two functions here. And we're going to compute f minus g of x. So that equals f of x minus g of x. So I substitute into that, right? F of x is x cubed. And now I'm going to subtract g of x, and g of x is x minus 1. When I get rid of the parentheses, notice my sign change right there. And I arrive at that result. All right, so it probably wouldn't surprise you to find out that the next two possibilities, the next two operations we're going to define for functions are going to be multiplication and division. And likewise, it probably wouldn't surprise you to see this. To define multiplication, we're just going to put the multiplication symbol in place of the subtraction symbol we just had. So in other words, f times g of x equals f of x times g of x. So if we go to part C of our example, oops, got ahead of myself there. We're asked to compute f times g of x. It is defined to be f of x times g of x. So let me just substitute right in there. Right, here's my g of x in the parentheses multiplying my f of x. If we multiply this out to simplify, we arrive at this polynomial. And finally, division. I think to no one's surprise at this time, we're going to replace the multiplication sign by the division sign, the fraction sign. In part D, we are asked to compute f divided by g, the function f divided by g of x. So we're going to build a fraction. F of x becomes the numerator of that fraction. G of x becomes the denominator. And there it is. Notice in the domain we cannot have x equals 1 because it would cause the denominator to go to 0. So I could write that idea down this way. The domain is all reals not equal to 1. In the other three parts, since we weren't doing any division in any of those calculations, there was no restriction on the domain. All right, you might be wondering, why did you do this? What does it come in handy for? Why would somebody invent this? Well, there's a good example, example 3. It's a modeling example that involves operations with the functions, and it's covered with a great video in your My Math Lab, your MML. So I have assigned it for homework, and you can work through that little video and get a nice explanation there. For right now, let's go ahead and try one of these on our own. Let f of x equals 3, the constant function 3, it's a horizontal line, and g of x equals x squared minus 1. Go ahead and find f of x minus g of x.